Hello, everybody. We're going to be looking at part 2 here, which is predicting Bronsted-Lowry reactions. So we're going to look a little bit at the strength of acids and bases. Here we have the reaction of CH3COOH reacting with H2O, which we have an amount of 100, and this reaction goes to 100.1.3%, which means of the base, we're going to get 1.3% and 1.3% of that. At equilibrium, only 1.3% of the CH3COOH molecules have reacted with water. This implies that the ability of the CH3COO- part of the acetic acid molecule to keep it as a proton is much greater than the ability of H2O to attract the proton away. So the comparison they have here is that we have a tow truck and we have a pickup truck, and they're both pulling on that H plus molecule here. And what happens is that most of it's going to want to stay with this. However, though, this H will want to pull it away and have that acid be formed. This means that CH3COO- is a stronger base. It has a greater attraction for protons than H2O. So we have something like HCl reacts with water, produces H3O plus and Cl minus. When HCl molecules react with water, the Cl minus of each HCl molecule has a much weaker attraction for its proton than any colliding water molecule has. The water molecules win this competition for protons overwhelmingly, and at equilibrium, essentially all of the HCl molecules have lost protons to water molecules. So remember, the stronger the base, the more it attracts another proton, and stronger the acid, the less it attracts its own proton. So something like HCl, we know that when we react it in water, it will ionize and become H3O plus and Cl minus. Whereas, if we can look at the example of CH3COOH, it's going to go back and forth here. It's going to be at equilibrium. So it's not going to go 100%, whereas this is always going to go 100%. Quick note, strong acids, strong acids ionize 100%. Those are the top 6 acids on your acid base table. So your acid base table looks something like this. You have all your acids over here, and then your acids are here, bases are here. Your acids go from strong to weak, and your bases go from strong to weak. We're going to talk about why this is here throughout this section of the equilibrium acids bases unit. And like I was saying, those strong acids are up here, and you pretty much only have one base, which is hydroxide, which is found down here. So that's where your strong acids are. This is where your strong bases are. So we're going to look at the table of relative strengths of acids and bases, which is what I was just talking about. And the table on page 8 of your data booklet ranks acids from strongest to weakest and bases from weakest to strongest. All right, so as I said, all these ones here are your strong acids. Hydronium's kind of an exception, so more of our product. And then from oxalic acid down, these are our weak acids. So the table's been built on empirical evidence. It's essentially been made off the fact that experiments have been done, and this has been proven that this is what it is. This table allows us to predict the position of an equilibrium in a reaction between an acid and a base. So here we're looking at the reaction of H3PO4 and H3 aqueous to produce H2PO4 minus and NH4 plus. So does the reaction favor the reactants or products? Well, I'll tell you right now, this reaction is greater than 50%. which means that its Kc is equal to greater than 1. Now, essentially what we can do is we can look at this and we can say, okay, we do not have NH3PO4 on our table, but what we know is that if our acid is above our base, then at equilibrium, we have over 50% of our reaction, which means that it favors the product, which our Kc is going to be greater than 1, as we have here. If our base is above our acid, this is going to be less than 50%, which means that the reactants are favored. Our Kc is, wrong way, less than 1. And H3O plus or OH minus, these are going to go greater than 99.9%. So they're pretty much going to go 100%. And we can show it this way because that 0.1%, but for the most part, our Kc value is going to be a huge number. As you can see here, the K, we're going to talk about what the Ka is shortly. We're just working with Kc for now, which is our equilibrium constant. The Ka is essentially our equilibrium constant when we're dealing with acids. And with that is that when we have that huge Kc, the reaction is going to the products 100%. 1, if it's at 1, then it's a 50-50 split. Greater than 1 favors the product, less than 1 favors reactants. All right, predicting the position of equilibrium in an acid-base reaction. According to the Bronsted-Lowry concept, a proton will only transfer if an acid entity collides with a base entity that is a better proton attractor than itself. The Bronsted-Lowry theory suggests that the predominant acid-base reaction should be the one that involves proton transfer from the strongest acid to the strongest base present in the system. So we have a few steps here for listing steps to predicting an acid-base reaction. So step 1 is listing all our entities present as they exist in aqueous solutions. So ionic compounds dissociate, weak acids don't ionize, strong acids form the hydronium ion and a conjugate base. So if we had something like HNO3, we wouldn't write it as that. We would write it as H3O plus and NO3 minus. Step 2, we use the entity lists of the relative strengths of aqueous acids and bases table to identify and label each entity present as a Bronsted-Lowry acid or base. So amphi protic entities are labeled for both possibilities. Metal ions are treated as spectators. Step 3, we need to use the order of the entities and the relative strength of aqueous acids and bases table to identify and label the strongest Bronsted-Lowry acid, the highest one on the table, and then the strongest Bronsted-Lowry base, the lowest on the table that are present in the solution. Step 4, write a balanced equation to show a proton transfer from the strongest acid to the strongest base. And then step 5, predict the position of equilibrium, whether it's going to be favor the products or it's going to favor the reactants. So we know here, going to favor products. This will favor reactants. Have some examples here. I'm going to let you look at 2 of these. I'm going to do one of them though, in which we have hydrofluoric acid and an aqueous solution of sodium sulfate are mixed. So we have hydrofluoric acid, which is HF. Acids are aqueous. We have sodium sulfate. When we have an ionic compound, we're going to split the ion up into cations and anions. So we have Na plus. We have SO4 2-, aqueous. We have H2O, which is liquid. So hydrofluoric acid is my strongest acid. We'd find that from our data booklet. And then we have H2O, so which could act as an acid or a base. But not only is SO4 2- a base, it is also our strongest base, which we would find out in our data booklet. All right. So when we write this out, we have HF, which is aqueous, reacts with SO4 2-, which is aqueous, And when we look at this on our data sheet, what happens is we find out that it is less than 50%, producing the F- ion in aqueous form and HSO4 minus also in aqueous form. I'm going to let you take a look at number 1 and number 2. And with that, that concludes part 2 of topic 2.